Okay. Today is still about Gaussian quadrature. Gaussian quadrature is a formula of this form. Here, W, we call it a weight function. We assume in Gaussian quadrature, W is continuous and positive, because only when W is positive, we can obtain some good results. In this formula, A and X, they are free to choose. We choose them so that the approximation is exact for all the polynomial f in this set. This set means the set of all polynomials of degree not greater than 2n plus 1. We want this approximation become exact for all polynomials of degree not greater than 2n plus 1. How to determine A and X? One approach is plugging the basis polynomials. Polynomial, the degree not greater than 2n plus 1. So there are 2n plus 2, so many basis polynomials. Then we have 2n plus 2 equations. Those equations can determine the 2n plus 2 unknowns. But the problem is that the resulting linear system, the resulting system is a system of nonlinear equations. And also, each equation involves powers, right? Say when I plug in xn, for example, x to 2n plus 1. Okay, here, then we get xi 2n plus 1. So in the front, there is a ai summation I from 0 to n. Yeah. So by hand, it is impossible to solve the system. We have to use a computer. But because the equations involve powers, even though we use a computer to solve the system, even though we get the result may not be accurate, because a power could be very, very large. So plug in the basis polynomials to determine the unknowns. This approach is not a good method. So we turn to another method. Okay. Then how to determine A and X based on one theorem. Okay. Let me repeat that theorem. Before the theorem, there is a lemma. Let me see. The lemma says that let Q be a polynomial of degree n plus 1. A polynomial of degree n plus 1 has n plus 1 zeros. Then this polynomial is W orthogonal to all the functions in this set, the set of all polynomials of degree not greater than n. In the following sense, in the sense Q times P. P is from this set times W, integral from A to B. It is 0. Okay. Where P is any function, any polynomial in this set. That means that for any polynomial of degree log greater than n, we have this integral is 0. Then we say that Q, this polynomial, is orthogonal to all polynomials of degree n log greater than n. Okay. There are some nice properties about this orthogonal polynomial Q. Okay. It turns out that the n plus 1 zeros of Q, they are all real numbers and also distinct and also lie in this interval. So the zeros of Q are candidates for the loops in Gaussian quadrature. Then based on this lemma, in the last class, we have this theorem. Okay. Let Q be the polynomial in the lemma, be a polynomial of degree n plus 1. Then is W orthogonal to this set, to all the polynomials of degree log greater than 1. Okay. If we choose the loops x0, x1, xn to be the zeros of this polynomial Q, and choose the coefficients A, okay, and choose AI. W times the cardinal function in Lagrange interpolation. Yes, dx. Then the formula here, the formula 1. Then 1 is a Gaussian quadrature. That means that the approximation is exact for all polynomials of degree log greater than 2n plus 1 is Gaussian quadrature. Okay, now theorem is here. This theorem tells us how to determine the logs and the coefficients in Gaussian quadrature. Now, the next question is how to find orthogonal polynomial Q. Okay. This is the first topic today. Yeah. Topic 1. How to construct orthogonal polynomials. This is a topic in section 6.8 in the book. Okay. Yeah. Topic 1. Now, topic 1 today. First, in this space, the space of all continuous functions defined on the closed interval AB, we introduce the following inner product. Function f from this set, function g from this set, inner product. Okay, the notation. Yeah, defined to be this integral f x times gx times w. Of course, here w, I assume greater than 0, greater than 0. Yeah. This is a inner product. This quantity satisfies all the properties in the definition of an inner product. Okay. Recall that in RN, say in RN, RN has a lateral inner product, the Euclidean inner product. Okay, Euclidean inner product. Take a review about the Euclidean inner product in Rn. A vector from Rn, second vector from Rn. The inner product is first entry of x times first entry of y plus second entry times second entry of y, and so on. This is an inner product. We call this inner product Euclidean inner product. From linear algebra, we know that. We know, okay, vector x is orthogonal to vector y. The angle between these two vectors is 90 degrees. If and only if inner product is 0, right? From linear algebra. Now, similarly, okay, here we say that function f from this space is orthogonal to function g. What it means? That means that if and only if this inner product is 0, is 0. Yeah. So go back to the lemma. Yeah. Actually, this is the inner product of Q and P. Yeah. Inner product is 0. We say that Q is orthogonal to P. Okay. Okay. Now, next, I present a process to construct orthogonal polynomials. Okay. A process to construct orthogonal polynomials. Right? We need orthogonal polynomials in order to have the roots in Gaussian quadrature. Okay. Step 1, set Q, here I use P, okay, according to my notes. P negative X 0. P 0. Yeah. 0 is degree. It's 1. Okay. Then from P negative 1, P 0, we can construct P2, P1, orthogonal polynomial of degree 1. Then from P0, P1, we construct P2, and so on. The formula is here. Pn is equal to x minus x variable. An, a number, constant, times polynomial, the periods orthogonal polynomial, Pn minus 1. N minus 1 degree, okay, degree of the polynomial, minus Bn, a constant, times Pn minus 1. Pn minus 2, not minus 1. Minus 2, x. Okay. Okay. Where n greater than or equal to 1. Okay. Then what are An and Bn? Where An is computed by this equation. X times Pn minus 1. Pn minus 1. Inner product. Yeah. Inner product definition is here. Yeah. Here. Inner product. That means that take integral. Take integral. Then over Pn minus 1. Pn minus 1. Inner product. Bn. What is Bn? Bn is x Pn minus 1. Pn minus 2. Inner product. And Pn minus 2. Pn minus 2. Okay. Yeah. So in this way, we have a sequence of polynomials. Those polynomials are orthogonal to each other. Okay. All right. Let me show you one example about this process. Okay. Say for example, take a look. Example 1. Okay. How about that? There is a W, the weight function greater than 0. Okay. How about for simplicity, let the weight function be 1. How about the interval AB? AB is negative 1, 1. Okay. Okay. Now let me construct orthogonal polynomials. Right. Then P negative 1 is 0. P 0 is 1. Now from this equation, I have P1. What is P1? Then from this equation, P1 is equal to x minus A1 times P0. 1. N is 1. So N minus 1 is 0. Minus B1. P. N is 1. So 1 minus 2. Negative 1. Yeah. But by assumption, this guy is 0 and this guy is 1. So therefore, P1 is just x minus A. Okay. Now let me compute A1. Okay. What is A1? A1 by formula here, it is inner product x n is 1 times p0. P0 is 1. P0 over P0. P0. Then inner product is an integral. Okay, so the numerator is this integral, negative 1 to 1. Then P0 is 1. Yeah, don't forget. Yeah. This guy is equal to 1. This is equal to 1. So the product of these two functions is just x. Then w is 1. So dx. Yeah. The bottom is P0 is 1. So the bottom is negative 1. 1 dx, right? X is an odd function. Odd function, and the integration interval symmetric about the 0. So integral on the top, 0. Integral at the bottom is equal to 2. So 0. So A1 is 0. So we get x. The first orthogonal polynomial is 1. The second is x. Now, from P0, P1, I compute P2. P2 by formula, set n to 2. Then we get x minus A2 times P1 minus B2 P n minus 2. Now n is 2, so P0. P1, now below it, it is x. So x minus A2 times x minus P0 by assumption, it is 1. So B2. Now let me compute A2 and B2. A2, what is A2? By formula, A2 is x times P1 and P1 inner product over P1 inner product. So the top is this integral. X times P1. This is x times P1. P1 is x. W is 1. So the bottom is integral P1 times P1. Yeah. P1 is x. So this is x. So therefore, this product is x to the third, an odd function, right? Odd function. The integration interval is symmetric about 0. So therefore, numerator is 0. And denominator, you can compute denominator. This is x squared. But anyway, this is 0. Okay. So A2 actually is 0. How about B2? B2 is x P1 P0 inner product. P0. So the numerator is this integral. X times P1 times P0 dx over integral P0 times P0 dx. So P1 is x, P0 is 1. So the top is x squared dx. And the bottom is P0 is 1. Yeah. So the answer is 1. Okay. So therefore, the third orthogonal polynomial is here. A2 is 0. So the first term, x squared, minus B2, 1/3. Yeah. This is orthogonal polynomial of degree 2. Right. Similarly, the next few orthogonal polynomials are similar in a similar way. P3 is equal to x to the third minus 3, 5, x. P4 is equal to x to the fourth minus 6 over 7 x squared plus 3 over 35. P5, it is x to the 5th minus 10 over 9 x to the 3rd plus 5 over 21 x over 21x, and so on. Okay, and so on. Yeah. So by that process, you can construct. Okay. Theoretically, you can construct orthogonal polynomial of any degree. Okay, any degree. Okay. Now this is an example 1 about how to use this formula, this process. Okay. Now, second, let me construct Gaussian quadrature. Okay. Second example. Example 2. Example 2. We have orthogonal polynomials now. Then I can tell Gaussian quadrature. Second example. Find the Gaussian quadrature formula. Quadrature rule. When W is 1, because we have orthogonal polynomials corresponding to W being 1. Okay, so I set W1, and the interval AB is regular 1. In Gaussian quadrature, let me see. We have n. N is n plus 1 is the number of roots. Now I set n to 2. Okay. N is 2. Okay. Okay. Then the Gaussian quadrature, the Gaussian formula, the Gaussian quadrature rule is integral. A is negative 1. Yeah. AB. So negative 1 to 1. F times the weight function. Weight function is 1. So yeah, roughly is A0 F x0 plus A1 F x1 plus A2 F x2. Okay. X0, x1, x2 by theorem. By the theorem here, the lobes are the zeros of orthogonal polynomial Q, degree 3, because the n is 2, so n plus 2 plus 1, 3. Yeah, the lobes are the zeros of orthogonal polynomial of degree 3. Okay, we got it, degree 3. What the polynomial is degree free. Yeah, here. Yeah, this guy. This is a orthogonal polynomial of degree free. Okay, now let me find its zeros. Okay, set P free equal to 0 and solve this equation. Then polynomial of degree free has 3 zeros. A factorization. So the 3 zeros is x is 0, right? X is 0. Then the other 2 roots is x squared minus 3 over 5 is 0. So the other 2 roots is 3 over 5 square root negative. Yeah. These are the roots for Gaussian quadrature. So therefore, I plug in the zeros. A0. I think it doesn't matter which point is which 0 is x0. So let me pick 3 over 5 square root as x0. And then A1, x1 is 0. Then A2, F. Yeah. Now, next, how to determine A0, A1, A2? You can use the method of undetermined coefficients because this is a Gaussian quadrature. The approximation is exact for all the polynomials of 2n plus 1 the degree. Now n is 2, 5. All polynomials of degree log greater than 5 make the approximation exact. So I can plug in 1. 1 is a polynomial. Plug in x squared into this formula. Then we have a system of 3 linear. Now this time, because we know the roots, so this time linear equations for the unknowns A0, A1, and A2. So we can tell. Or if you don't use the method of undetermined coefficients, you can use this formula in the theorem. Yeah, the theorem. Theorem says that the logs are the zeros of orthogonal polynomials, and the coefficients AI can be computed by this integral, or you can use this. Okay, but anyway, use either method, then we get the coefficients are A0 is 5 over 9 negative 3 over 5 plus 8 over 9 F0 5 over 9 F negative square root of 3 over 5. Yeah. This is a Gaussian quadrature for n is 2, and also for this special interval and special weight function. Yeah, Gaussian quadrature, very, very popular. Okay, yeah. Actually, in my research, I often use Gaussian quadrature, very accurate, highly accurate. Okay, now second topic. Let me present some properties about Gaussian quadrature. Okay, about Gaussian quadrature. Yeah. Topic number 2. Convergence and error term in Gaussian quadrature. Okay. Okay. Some properties. Okay.
The first result, film, okay, film. In a Gaussian quadrature, it turns out that all the coefficients AI are positive, okay, positive. And the sum of the coefficients I from 0 to n is equal to this integral a b w. Yeah.
Okay. The proof is simple. Okay. Yeah, simple. Okay. Gaussian quadrature
Is here. Yeah. Summation I from 0 to n AI f xi. Okay.
Yeah. The approximation is exact for all polynomials with degree log greater than 2n plus 1. Okay. Now, okay. In particular, I said f the Li square, Li cardinal function, Li square. Li square, Li actually is equal to 1 when x is equal to xi. 0 when x is not equal to xi. Right? Do you remember? Okay. Now, in Gaussian quadrature, I plug in this in S. Hey, Li, the degree is n. Li square degree is 2n. So 2n, degree 2n. So the approximation is an equation. So plug in Li square here. Then we get A, B, Li square times W
equal summation I from 0 to n AI L. How about I use a different index here? Say K, K. So summation LK XI.
But because only when I is K, the term is non-zero. When I is not K, the terms are 0. So actually this sum is AK a square. I mean a square. LK square XK. But LK XK is equal to 1. So AI. How about the left hand side? W greater than 0. And this guy, at least at some point is 1. So area integral is area. So area under the graph of this product and above x-axis, the area cannot be 0 because the integrand is non-negative and at some points non-zero. So this number must be greater than 0. So we have proved that all the coefficients are positive. Then how to prove this equation? Easy. Set function equal to 1. 1 is a polynomial. Of course, degree less than this. So plug in 1 in this Gaussian quadrature. Then we get integral AB W dx left side now equal
equal summation I from 0 to n.
Function f is 1, so AI. So the sum of the coefficients of Gaussian quadrature is equal to this integral. Yeah. So this is a first property. Okay. Nice. Okay. Very nice. Yeah. Second property about the error term. Okay. Yeah. Theorem 2. Yeah. You can find these theorems in the book. Consider a Gaussian quadrature
with error term. Yeah. Integral a b f w. Yeah, we always assume w greater than 0. Okay. Summation I from 0 to n ai times f xi Gaussian quadrature. Now, to make the approximation exact, we need to add an error term. Okay. Yeah. Error term. So pass error. Okay. Then what the error is? Okay. For suppose a function f is smooth enough, it is in this set 2n plus 2 over some open interval CD, where CD contain this interval AB. That means that the function f has derivative of order up to 2n plus 2. Okay, and all the derivatives are continuous over some a little bit larger interval than the interval AB. Okay, then we have the error term. Error term is 2n plus 2. Take derivative 2n plus 2 times on function f and evaluate at some point psi. Then over 2n plus 2 factorial integral AB q square times w. Okay. Where sine it is upon in the open interval AB. How about q? And q is this product. That means that x minus the log x0, x minus second log, and so on. X minus x. This is the error term. By a mean value theorem for integral, because this guy doesn't change sine over the interval AB, we can move W outside. 2n sine 2n plus 2 W outside. Okay, a second sine. Okay, then integral AB. Yeah, Q actually is a polynomial, so take integral on the polynomial. Q square. This polynomial degree is n plus 1. So Q square, the degree is 2n plus 2. Take integral. So the degree is a 2n plus 3, right? Take integral, right? Take integral. And then plug in AB. Then this is order b minus a to 2n plus 3. Yeah. So if the interval a to b is a small interval, that means that b minus a, the length less than 1, then this number is very, very small, very, very small number. Okay. So Gaussian quadrature is order 2n plus 3 formula. So this is very, very accurate. The third theorem. Theorem number 3. Actually, for each n, each n, n is a 0. How about let me use hn 0 from this set 1, 2, 3, and 4. For hn, we have a Gaussian quadrature formula, right? Yeah, roughly it's a summation I from 0 to n. Now, coefficients, of course, depends on n. And the logs also depends on n, right? You agree? Yeah. For each n, say in the previous example, n is 2. We got a Gaussian quadrature. N is 3. We got another Gaussian quadrature, right? From the orthogonal polynomial of degree 4, right? N is 4. Then from the orthogonal polynomial of degree 5, we get another Gaussian quadrature. Okay, now this theorem says that if function f is continuous over the interval AB, then the right side is a number. This is a number. The limit as n approaches infinity, exactly the left side. For each n, from the right side, we have a number. So we have a sequence of numbers. Those numbers approaches this integral. This is the third theorem. Let me stop here. Yeah, how to stop? Okay, let me stop here. Any questions about today's class?